So as we've seen, thermodynamics is very important in determining whether a reaction will happen. We just discussed all of enthalpy and the change of heat and how it is important in determining if a reaction is possible. In addition to that, we have the second law of thermodynamics, which also determines if a reaction is possible. And it states that all processes increase entropy, which is the degree of disorder or chaos within the system. I provided some examples of this in the first week of class when we talked about entropy. Entropy is increasing disorder. We talked about the ottoman, and when the ottoman lid is open and all the toys are all over the living room is in a state of chaos or disorder. But when all those toys are back in the ottoman and we put the lid on and it's one nice clean structure, that means we have a decrease in entropy. We have decreased disorder within the living room. So energy change in a system can also be defined by its entropy. So the order or disorder of the molecules in the system. The higher the disorder, the lower the energy in a system. The lower the disorder, the higher the energy. So there's something called an inverse relationship, that when disorder is really, really high, the energy is low. And then when disorder is really, really low, energy is high. So they're the opposites. So you got to remember that. Okay, it's the opposites. When there's high disorder, high entropy, there's low energy. When there's low entropy, there's high energy within the system. Entropy, meaning the disorder or chaos within the system, can be represented by the symbol S. Now, this isn't as intuitive as enthalpy, which is the change in heat, being H. Okay, so this is just something you have to remember, that entropy, change in disorder, is denoted by S or delta S. And entropy its units are in joules per degree Kelvin. Now, Kelvin is the standard international unit for temperature. Similar to enthalpy, entropy can also be lost or gained by a molecule. So let's go back to an example of eating an apple. You're eating a solid apple. It's going through your esophagus, down into your stomach, undergoing digestion, being blasted apart into many, many thousands of molecules. And then it's getting basically put into a glucose, the monosaccharide glucose, and being converted into ATP. So as that happens, the process of digestion is blasting apart a food into millions of molecules. We're increasing disorder. So this is how a system has increased or gained entropy. It's gaining disorder is in the process of digestion. Meanwhile, with that food, say you have glucose, and we don't have to produce energy right away. We can store that glucose in the form of glycogen. So now we're building, we're binding, we're making disaccharides and polysaccharides to be stored as glycogen. So that would be a system is losing entropy. It's becoming more ordered. So the process of digestion and biosynthesis is two examples of how entropy can be lost or gained by a molecule in biochemistry. So entropy is affected by three factors. One is the arrangement of molecules, two is the number of molecules, and three is the motion of molecules. So let's talk about each of those now. So the first factor that affects entropy is the arrangement of molecules. If we have a tight arrangement, like the picture shows on the left, where we have a 5x3 arrangement that's very tight, we have less disorder or less entropy compared to a loose arrangement, which is on the right, where the molecules are all spread out. This has more entropy. Okay, there's more disorder within a system. The prime example I have is a toy chest or the ottoman I gave before, where when all the toys are in the toy chest, it's in a tight arrangement, the molecules are in a tight arrangement, there's less disorder. But as soon as that toy chest is open and the toys are all over the room, it's scattered everywhere, and there's really a lack of arrangement, then there's going to be more disorder and more entropy. So when it comes down to the arrangement of molecules, it also is related to the state of the molecule. So an entropy that is solid has less entropy than a liquid, which has less entropy than a gas. So a solid, and it makes sense because a solid like an ice cube is more tightly arranged. It has less entropy than if you were in a liquid form, than if it was in a gaseous form where there's more molecules and more randomness. Another example of this arrangement is crackers in a box versus poured out on the table. Crackers that are in a box are in the box. They're nicely organized and arranged in that box. However, when they're poured out on the table, they're all over the place. And so this increases the disorder. From a biochemical standpoint, another example would be glycogen versus glucose monomers. If we have tons of glucose monomers after digestion, all in the blood, then we have a huge disarray of arrangement. We have a loose arrangement, and as a result, we have more entropy. But as we build those glucose monomers together and form those glycosidic bonds to create a polypeptide and then a larger molecule of glycogen, we're actually decreasing entropy. The second factor that affects entropy is the number of molecules, such that the more molecules we have, the more entropy there is. The less molecules, the less entropy. A prime example of this is a kid's birthday party. When there's only 1 or 2 kids at the party, it can be well controlled and it's not disordered. But as soon as there's 8 to 12 kids at a kid's party, there's a huge amount of disorder within the house. So the more kids there are, or more molecules there are within a system, the greater the chaos, or greater the randomness, or the disorder. Now let's talk about this from a biochemical standpoint and look at the equation that's in the middle of the screen. What is the molecule on the left? It is a disaccharide, and you should be able to name it. So first of all, let's look on the far left at the monosaccharide. And we can see when we count the carbons, we go to the C4 carbon, the carbon number 4, and we see that the hydroxyl group is pointed upwards. So we know automatically that that monosaccharide is known as galactose. Then if we look at the molecule on the right, we can see that on the C4 carbon, the reaction would be that hydroxyl group is pointed downwards. So we knew that's glucose. So we have a glucose and a galactose molecule bound together with a glycosidic bond through a condensation reaction. We know that this is going to be lactose. So when we break down lactose using the lactase enzyme into the 2 individual molecules, we're increasing the number of molecules, and therefore we're increasing entropy within the system. So whenever we have to break down something in a catabolic state within the body, we're increasing the number of molecules and we're increasing the entropy. We're becoming more disordered. Okay, so digestion is an example of this. The breakdown of glycogen or any polysaccharide where we're releasing more molecules in the system. That means we're increasing entropy, as well as fatty acids in the blood versus being stored as a triglyceride. So being nice and arranged as a triglyceride, we have less molecules free. But as soon as we break down a triglyceride and release the fatty acids into the blood, we're increasing the number of molecules, and then therefore we're increasing entropy within the system. The last factor that we're going to talk about that impacts entropy is the motion of molecules. So when we have more motion, this means that there's more disorder within a system. When there's less motion, we have less disorder in a system. And it's very much related to pressure. So if we look at the 2 pictures here, we have a container that's enclosed with 7 molecules in it, which is smaller. And then we have a container that's larger with the same 7 molecules in it. Okay, so this is where we see a change in the pressure. The smaller container with 7 molecules in it has higher pressure, while the container that is larger with 7 molecules has less pressure. So the more pressure, if we look at that little container, has less motion because there's less room for those 7 molecules to move. And therefore it has less entropy. And because we defined the relationship between entropy and energy as being inverse, such that when we have high entropy, we have low energy. And when we have low entropy, we have high energy. They're opposites. So when we have less entropy, that system will have more energy. Okay, likewise, when we have that bigger container with still 7 molecules in it, But now that you have more area to move, because there's less pressure within the system, we have more motion. And more motion brings more disorder, more entropy. And as a result, there's going to be less energy. Okay, the pressure of the small bottle with 7 molecules versus the pressure of the large bottle with 7 molecules. Higher pressure means more energy. This is a hard concept for many students to understand, so make sure you take some time to understand this, that the more motion means more disorder within the system, and it is related to pressure. To calculate the change in entropy, we can represent it with this equation. The change in S, or entropy, equals the final entropy of the molecule minus the initial entropy of the molecule. So when the delta S is positive, the final entropy of the molecule is greater than the initial entropy of the molecule. So that molecule is becoming more disordered. When the delta S is negative, the final entropy of the molecule is lesser than the initial entropy of the molecule. So the molecule has become less disordered. So a prime example of when delta S is positive is in the process of digestion. When we're breaking down a solid food like an apple into hundreds of thousands of glucose molecules, the system is becoming more disordered. It has a positive delta S, and the molecule has a greater entropy in its final state than in its initial state. In contrast, when delta S is negative, is when, for example, in your body, you're using the amino acids found in food to make a biological protein. So we eat food that has protein, we break it down to its individual amino acids, and then say we need to build an enzyme within our body for functioning. We have to combine those amino acids, string them together with peptide bonds to create a biological protein. That's where many molecules are coming together to form one larger molecule. That's an example of when delta S is negative. We're decreasing entropy, decreasing the disorder within a system. This slide provides a lot of examples of entropy. What I want you to do is figure out what are positive and what are negative types of entropy. And we will take this up at the beginning of class in our synchronous lecture this week. Now let's do a quick learning check. Which one word is most synonymous with enthalpy? Endothermic, exothermic, energy, or heat? You should automatically pick heat. When you think of enthalpy, it should be the change in heat, or you're looking at the heat within the system. So the key word, when you see enthalpy, it's heat. The next question is, which one word is most synonymous with entropy? Disorder, number, state, or motion? You should automatically think of disorder. Entropy should be affiliated with disorder, enthalpy with heat.